Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper, Charlie to friends, and I'm a theoretical physicist currently doing a postdoc over in the Helsinki Institute of Physics in the University of Helsinki in Helsinki, Finland. And I'm a cosmologist, so that means that I study the universe, the contents of the universe, how things evolve, how things interact, cool stuff happening inside the universe. I love being a cosmologist. It really is an amazing job. I get to work on some really, really cool topics. And I love chatting to everybody about all of the cool things I get to work on. So for anybody who doesn't know, Cup of Cosmology is an interactive stream. The idea here is that you people can ask me anything you want about science, about cosmology, about physics, about academia, anything you want, and I will do my best to answer your questions. I won't always have all the answers, but I will do my best to tell you when I do know the answers and when I don't know the answers. If you're a first-time viewer, welcome. If you're a regular, welcome back. It is great to see all of the regulars coming in. I see we have Mita, we have Shawnee, we have Ange, Lethargo, John, Prath, Scott. Great to see everybody joining here in the comments. Really nice to see so many regulars coming in. And if you're a first-time viewer, welcome. Great to have you here. If you haven't done so yet, there's a nice subscribe button you can click on YouTube to make sure you never miss my live streams. And please do like this video, leave a comment, do all of the usual YouTube stuff, or Twitch if you're watching on Twitch. It really does help boost engagement, and then I can chat to more people about the amazing stuff that's happening inside the universe. Today we do have a topic planned. There is a topic today. It's not going to be a general ask me anything. There is a topic, and I got to give it the very catchy title of Hubble Troubles. So I'm going to come to that in a minute. Hey Nina, great to see you over from Mastodon. Great to see you here as always. Nice to have people coming from different places. Great to see you all here. Wherever you're watching from, feel free to leave a comment, say hi, and let's get the conversation going. And just to comment that this video is indeed 1 week late. So I kind of advertised that I was going to do this last week on September the 22nd. And then last week I actually cancelled the stream because, as some of you know, I am chronically ill and sometimes my energy levels just don't allow me to come on and do these live streams. So sometimes I have to cancel and sometimes that's on short notice. So some of you might have seen last Sunday the stream did appear, and then half an hour before I went live it disappeared. And that's going to happen sometimes. So the easiest way to make sure you know if I'm live or not is just subscribe to the channel. And then you will always know if I'm going to be live or not. But yes, apologies for not being online last week, but I'm here now. So today we get to do the Hubble Tension, Hubble Troubles, and everything related. Hey, Abyss, great to see Abyss here in the chat. Abyss, we know each other from the early Periscope days years ago. We've done some streams together in the HAPS days. Great to see you here, Abyss. And yeah, it's normally you come in towards the end. It's great to see you come in towards the start this time as well. Comment from Scott here that you actually have 3 questions, but none about Hubble. Well, you're welcome to ask them, but I probably will ignore them today because I do want to stay on topic. And today's topic is the Hubble tension. So if you have questions that are not related to the Hubble tension, feel free to ask, put them in the comments. But I probably won't reply to those today because I do want to say somewhat focused, somewhat on topic. Although, as all of you know, I'm very bad at staying on topic. Why stay on one topic when you can stay on 20? That's how my brain likes jumping about. Comment from Abyss, you hope I'm feeling better now. Thank you, I am. So I have long COVID, and this means that sometimes I get energy crashes, and I basically have chronic fatigue. And sometimes that means that I don't have the energy to do the streams. Fortunately, these episodes are short-lived and normally last only a day or two. And over the last couple of months, these have been improving. So I cancelled the stream last Sunday because I started to feel a flare-up coming on, and I've learned not to push myself when that happens. But then it was gone in about 6 hours because I took care of myself when I had to. So thank you for the concern. I see I'm getting some people asking if I'm okay, if I'm feeling fine. I am feeling fine now. But when these episodes happen, I do have to cancel the streams, and that's just the way it goes. But thank you for the well wishes, everybody. And I know some of you did reach out like, hey, you were supposed to be online, you're not online. So thank you. I do appreciate you all reaching out. But don't worry, I am good to go today. As Chappelle Gone would say, I am HOTTOGO. This song has been stuck in my head for weeks. I apologize for the random pop reference. It's rare for me to make a pop song reference. Okay, so I feel like cosmic ladder is going to be discussed today. It is. It is. So there is a question already from James. What is the Hubble tension? So let's get started. The topic today is the expansion of the universe. So we've known for about 35 years now, since the 90s, which is a long time ago. We've known since the 90s or the late 80s that the universe is undergoing accelerated expansion. So not only is the universe expanding, it is expanding faster today than it was in the past. And in the future, it's probably going to expand faster than it is currently right now. So since since already over 100 years ago, in the time of Edwin Hubble, as Prath is just saying here, we know that the universe is expanding. This is something that was already shown by Hubble many, many years ago, 100 years ago, using data from other people as well, like Henrietta Swan-Leavitt was a great contributor to measuring Cepheids, which were used to measure the distance to supernova and show that the universe is expanding. But we have known for 100 years or more that the universe is expanding. So the universe is growing, it is getting bigger. But since 30 years, we know that not only is it expanding, it is expanding faster today than it was in the past. And this is likely to continue. So not only is the universe expanding, this expansion is accelerating. So this is when we talk about the expansion rate of the universe, we usually use one number to define the expansion rate of the universe. And this is the Hubble constant, named after Edwin Hubble, who was the first one to really propose in papers and really systematically study how fast the universe is expanding, or if the universe is expanding. And he introduced this constant, which is a number that appears in the equations that define the expansion of the universe. And it's just a number that tells you how fast the universe is expanding. Now, this Hubble constant has very strange units. It's in kilometers per second per megaparsec, which means it's not really a velocity, it's not a speed. It just tells you each patch of the universe expands at a specific rate. So if you take a 1 megaparsec chunk, which is the average distance between galaxies, if you take that chunk, it expands it with a specific speed. So it doesn't really have units of speed, and it's not really fair to think about this as the speed of expansion, but more of the rate of expansion. So the Hubble constant is this value that gives us the expansion rate of the universe, originally coined by Edwin Hubble many years ago in the 1920s. And it's something that 1920s, 1930s, around then. And now, since around 1989, we know that the universe not only is expanding, but this expansion is accelerating. And this is something that we can quantify, we can measure using the Hubble constant. So when we talk about the acceleration of the universe or the expansion of the universe, we are going to be talking about it in terms of the Hubble constant. As you're probably picking up by now, Hubble tension, what does Hubble tension mean? What does Hubble troubles mean? Basically, short version here, and then we have an hour to get into the long version. Short version here is, depending on how you measure the expansion rate of the universe, you get slightly different numbers. Slightly different is not a problem if they're still within range. If you say one is 5 and the other is 50,000, you're quite far off. But if they're approximately the same, it's good, but they're not same enough. They're not similar enough that we can say that they make sense. They're a bit too far apart from each other. So the different ways we go about measuring the expansion of the universe leads to different answers. And this is what is known as the Hubble tension or the Hubble crisis, the cosmology at a crossroads, the biggest crisis in cosmology, depending on how clickbaity you want your paper title to be. Hubble troubles is a nice one that rhymes, but the main thing we're going to be talking about today is how do we measure the expansion rate of the universe? Why are we getting different values? What does this mean for physics? And how does JWST help us with this? The reason we're doing this today, and I've seen there's a few comments I'm going to get to in a sec. So the reason we're doing this today is because there have actually been new developments within the last 2 months. So in August, there were 2 papers, 2 new publications discussing this topic from new perspectives, or kind of one came out and then the others have replied to this paper. But it's got the community really interested. 2 weeks ago, there was what is known as a rapid response workshop, where a bunch of people get together, a bunch of people in the field got together to discuss this. And it's a rapid response because there's a new result in the literature, we have to discuss it now. On this meeting I attended, it was organized online, had a bunch of experts presenting different perspectives, and 350 people, I think, turned up for a workshop that was organized very spontaneously. And it was very cool to see 300 experts on this topic get together and bash our heads and scratch our heads like, what is going on? But this workshop has prompted, and the papers, of course, have prompted a lot of interest. So this is what I'm going to talk to you about today. Going to the comments and the questions. There's a comment here by Prath. I'm going to jump around a bit. Kilometers per second per megaparsec. It's a megaparsec per second. Sorry, megaparsec. Yes, it's kilometer per second per megaparsec, approximately. Yes, that means it can be adjusted to megaparsec second megaparsec, aka 1/2. So the expansion of the universe can be expressed in hertz. Technically, yes. So once you cancel out units, yes, and this is why we can talk about it more of an expansion rate than anything else. Because what does it mean to talk about it in hertz? It makes sense when we look at how we describe the equations of the universe, the Friedmann equations. It makes sense. But yes, when we talk about the expansion rate, it is not a velocity, it is not a speed. It has units of megaparsec per kilometer per second or kilometer per second per megaparsec, whichever one you want. It's an interesting way of describing things. It's an interesting set of units. And that makes things a bit harder to conceptualize, but it really is just the Hubble constant tells us how fast the universe is expanding, or the expansion rate of the universe. Okay, going to comments, and then we're going to get straight into how we measure the Hubble constant, what are the numbers, what does this mean, and where we go from here. As always, jump in with your questions at any point. I will be answering the questions throughout. This is not just me monologuing. I will try to incorporate your questions as we go. So there was already the question from Prath that I tried to answer already. Does the Hubble tension come from Edwin Hubble's research on the expansion or measurements from the Space Telescope? Both. The Space Telescope is named after Edwin Hubble, but the Hubble constant comes from Edwin Hubble's work. But you'll see later that it relies on data from the Hubble Space Telescope, which is fun. Comment from Abyss about long COVID. It requires in-depth study. It does. One of the biggest problems with long COVID is that it is very new. It is still 4 years only since COVID happened, since COVID started. So trying to do any long-term studies, like, is long COVID something that's going to get better? How does it affect people? This is something that is very difficult to do because it is still very current and still very much ongoing, which makes it very hard to do any long-term studies. But there are studies coming out now, 2, 3, 4 years in, there are some studies coming out. And the results are very interesting, but yes, we need more research there. Okay, comment from Paul. Hi, Paul. I know you said you're watching from an airport. That is very cool. Hello. I missed your comment, but yes, you did say somewhere that you're watching from an airport. So have fun, have a good flight. So there was a comment here that you said you'll ask, just in case you drop out. Is it possible there's not a single number but varies by location over large distances, even in one epoch? Short version is yes, but we've studied that and it doesn't seem to be the case. But I'll get into that a bit more later. So that was just the short version in case you have to catch a flight. And I'm making a note of it, so I'll come back later. Short version is we've looked at that. It doesn't seem to answer the question. It doesn't seem to solve the troubles that we are having. Okay, as always, if you ask questions, ask at each other. I'm not going to read them. I assume if you start by tagging somebody else, you're having conversations, which is great. But then I just won't read them because I assume you're chatting amongst yourselves. So I just sort of follow up from Paul. I'm asking about whether the physical constant really is a constant or whether different parts of the universe. Okay, so on this note, we call it the Hubble constant, and it is pretty much constant in space today, at least according to all of our measurements. But the Hubble constant is actually not something that is constant in time. As I mentioned before, the expansion rate of the universe is changing. The universe is accelerating faster today than it was in the past, which means the Hubble constant is not actually a constant. We call it H naught, so H sub 0, where the 0 indicates we are making the measurements today. We are talking about how fast it's expanding today. But the Hubble constant is not constant in time. So at different points in the history of the universe, you will get different values for this. What we generally do is we plot what it would look like throughout the history of the universe, and then we get the value today. So even though we call it the Hubble constant, it is not technically a constant through time. But when we say the expansion rate of the universe today, then that is the constant that we're talking about. And of course, the concept of today is not the same a week from now as it was a week ago. Okay, still talking about the units of the expansion rate here with breath. So the acceleration of expansion can be measured in hertz to the hertz squared. and the jerk of the expansion can be measured in hertz to the 3. Yeah, I'm not sure if people have done that, but hypothetically, yes, you could. Okay, comment from John. Did it seem like the community accepts the new results that the Hubble tension isn't significant, or is it more controversial? It is controversial, and this is what we're going to get to. So ask me that again, or I'll answer that, as you will see as we get to the end of the stream. But nothing is ever easy in science. New results are always going to be met with skepticism, which is valid because this is how we do science. It takes time for new results to be scrutinized properly before we can accept them. So as I'm going to get to later, there is controversy in this topic. Is the Hubble Space Telescope finally broken? It is not. The Hubble Space Telescope is still taking data. It is still taking amazing data for us. It's had some issues. One of the reels is broken, but it is still taking amazing data for us. But we also now have the JWST, the Just Wonderful Space Telescope, which is also taking data and which has a much bigger mirror and is looking slightly different frequency ranges. They are very complementary, but JWST is definitely going further than what we were able to do with the Hubble Space Telescope. Okay, just some quick fire answers of the questions here. Back to the expansion of the universe. So of course, when I say the universe is accelerating, so not only is it expanding, but this expansion is accelerating, it is very fair to ask the question of how do we know this? How do we know that the universe is undergoing accelerated expansion? And the way this was so for years, we've been able to see that as galaxies get further and further away from us, they seem to be moving faster. So they seem to be accelerating. And this is or they seem to be expanding. This is what Hubble already saw 100 years ago, that objects are moving away from us. In general, the further out we look, the further away objects are moving away from us. So not only are they further away, they're getting further away. Then in the 1980s, 1990s, there was this big effort to try to measure the distances to these galaxies and see just how much they are expanding. And to do this, we use supernova. So supernovae are stars that have reached the end of their lifetime. A star that reaches the end of its lifetime is going to have a constant battle with gravity pulling things inwards and the pressure of the fusion happening inside the star pushing things outwards. So you have this constant battle. When a star reaches the end of its lifetime, it runs out of fuel to burn. So you get two things happening. It starts to contract slightly, then there's a pressure burst and everything explodes outwards. This is what is known as a supernova. It is an exploding star. All of the outer layers of the star are shoved outwards throughout the universe. And then what is left, the center of the star, collapses to form a black hole. So when you have a supernova, you have a star that's reached the end of its lifetime, collapses, or pushes out all of its outer layers in a massive explosion known as supernovae, and then it collapses and leaves behind a black hole. Not all stars will be supernova. They need to meet specific characteristics. But the cool thing about supernovae is they are extremely bright. If a supernova were to happen in our galaxy, we'd basically look like we have a second star in the night sky. It would be as bright as having a second sun. If it were to happen close by in our galaxy and we could see it, if it's the other side of the galaxy and blocked from our view, maybe not. But if it's within our view, it would light up the night sky very, very clearly. So supernovas are explosions, but supernovas behave in a particular way. We know supernovas are going to happen when a star reaches the end of its lifetime. We know approximately what is happening inside stars to cause a supernova. So, because we know what is going to happen inside supernova, they are something that are known as, supernova don't always leave black holes. They can also leave a neutron star. They can also leave a white dwarf, depending on how massive they are. Basically, they leave a massive core behind, but most of their outer layers are pushed away in the explosion. But because we know how supernova behave, we know approximately how much light they're going to release. And if we know how much light they're going to release, we can standardize this. Once we standardize them, we can use the amount of light we're seeing from the supernova to calculate how much light we didn't see, and therefore how far away they are and how much light was lost along the way. So supernova is what is known as a standardizable candle. We can turn it into a measuring stick. One way to think about it is if you have a light bulb that is emitting at 100 watts, if you're further away, the light bulb is going to seem dimmer because you're not, if you put a light bulb right in front of your face, probably don't do that. It's going to be brighter than if the light bulb is in the house across the street. Also, don't look into your neighbours' houses. My metaphors are getting weird today. But if you know that that's a 100-watt light bulb, you can figure out how far away you are from it based on how much light you are receiving. This is the same as what you can do with supernova. Based on how much light we're receiving and knowing the kind of standard of supernovas, you can figure out the distance. But it is not a straightforward process. There are several steps involved in making candles into a ruler. But the point is, you can use supernovas as candles. You can use this as a ruler to measure distances. Once you can measure distances to galaxies, and you know how fast they're moving away from us, which you can get based on how the light coming from there is distorted. We know that as light travels throughout the universe, its wavelength is stretched. So based on how much the wavelength is stretched and how far away it is from us, we can figure out how fast it's moving away from us. So using supernova, a group of people in the 1980s, 1990s, led by Adam Rees et al., were able to find that not only is the universe expanding, but this expansion is accelerating. So we live in a universe that is growing, and that it is growing more and more every time. This is why when we look at the standard diagrams of the history of the universe, which should be coming up on screen, but I've just changed my slide deck and now it is being slightly slow. So when we look at the history of the universe, there's always this thing where we have the accelerated expansion in the late universe, where we have this initial expansion, then it grows continuously, approximately, and then you have this expansion. So you have this accelerated expansion. So this is something we've known for 30, 35 years now. There was a Nobel Prize awarded for discovering that the universe is undergoing accelerated expansion, because this is also that we need something to explain this accelerated expansion, and that happens to be dark energy for now, our best explanation that we have. Okay, comment from Prath here. Wolfram Alpha tells you that the Hubble constant is 2.2 attohertz. Sounds about right. Yeah, sounds about right. Okay, comment from Abyss. What are the inherent flaws of standard candles with Cepheid variables in the cosmic ladder approach? Excellent question, Abyss. Let me get to that in a minute. When I get into details about the different ways we measure the expansion rate of the universe, I will answer that. So I'm just writing a note here of problems with Cepheid. So now that we know that the universe is expanding and that this expansion is accelerating, we want to measure this. We want to know how fast the universe is expanding. And there are several different ways we can go about doing this. There are several different approaches towards answering the question of how fast is the universe expanding. Sticking with what we were just talking about, we can use supernova to get this value of h0. But the way that we do the supernova measurement is not direct, because we need to be able to calibrate the supernova on something. The thing we calibrate the supernova on are Cepheids. So Cepheids are types of stars that have a specific brightness. They're kind of like cosmic lighthouses. Sometimes they're going to be brighter, sometimes they're going to be dimmer. They're going to be brighter, they're going to be dimmer. And this is something that is related to their distance. Based on how far away they are, you can figure out, so they have this period of rotation. This is related to the luminosity, so the amount of light they're emitting, and the amount of light they're emitting gives us the distance. So we have this kind of distance, period, luminosity relationship with Cepheids. Just a comment here that I was told a couple of weeks ago that I mispronounced the word Cepheids. I've since looked it up, and there's like 5 different accepted pronunciations. I use Cepheids. Some people call them Cepheids. Some people call them Cepheids. Different ways of pronouncing it. Cepheid stars. Okay, so the idea of Cepheids is they are these stars that have a specific brightness. We can use this to figure out how far away they are. So then we do a 3-step process. Step 1 is find Cepheid in a really, really, really close by galaxy. A galaxy that we can measure the distance to using other methods. For example, how the galaxy moves in the night sky. This is step 1. We find a galaxy, very close by galaxy, that we know the distance to, that has Cepheids. This allows us to calibrate step 1 of the process. And then we can say from us to this galaxy is this far away. This Cepheid has this specific brightness. So I now have an anchor point. This is step 1 of the process. Once you've been able to calibrate your distance-luminosity relationship for Cepheids, next step is to find galaxies that are a medium distance, close, but not that close. but you want galaxies that have both Cepheids and supernova. These are going to be galaxies that are close enough that you can distinguish individual stars, because you need to make out the Cepheids, but not too far away that they're out in the Hubble flow, as we would say, out there. So this is step 2. Step 1, you calibrate your Cepheids. Step 2, you use your Cepheids to calibrate your supernova. So you, first of all, you measure, you've always pronounced it Cepheids. Yes, this is the thing, Cepheids, Cepheids, whatever you call it, as long as we understand each other, it's fine. I gave basically this talk so I presented this new paper at our journal club recently, and I got 5 minutes in and someone stopped and was like, wait, is that the correct pronunciation? Have I been mispronouncing them? And then we had a debate about pronunciation. So can we get back to physics here? Let's just accept that language is fluid and evolving and everything is valid as long as we communicate. I have a sort of tangent about etymology that I'm not going to go into. The main point of language is communicating. As long as we're understood, it doesn't matter. Language is adaptable, fluid, and this is why you get fun new words, because language is evolving and adaptable. Okay, however you want to pronounce Cepheids, as long as we know what we're talking about. So, step 1, you use the distance to a known galaxy to calibrate Cepheids. Step 2, you use Cepheids to calibrate the distance to supernova. Step 3, you look at faraway galaxies that only have supernova, and you use the ruler that you've just constructed. You use this new measurement device to get the distance to these supernova. So 3-step process, using local measurements to calibrate Cepheids, using Cepheids to calibrate supernova, using supernova to measure the expansion rate of the universe. It is very cool, but it relies on several different things. Yeah, Germans probably pronounce it as Cepheidus. Might be. You know, I've learned about them in many different languages, and I still don't know how to pronounce them the right way. It doesn't matter. Okay, so this way of measuring the expansion rate of the universe involves several steps. It involves, first of all, the Cepheids and then the supernova. It is a lot of stuff that can go wrong. However, this is something that people have known about this technique for years. People have been working on this technique for years, and it is something that is a very well advanced technique. We know what the common problems are. Do we have the amount of metal in the Cepheids can determine this relationship, but the error on this is very small. The amount of dust in galaxies in between can affect this, but this is something we think we've understood. The way supernova behave, are they actually as standard as we think they are? This is also a possible source of uncertainty. So there's a lot that can go wrong in this measurement, but using Cepheids to anchor supernova is something we've been doing for many, many, many years, and it's something we have a good handle on now. Where does all this data come from? Up till now, from the Hubble Space Telescope. So the best measurements we have for supernovas calibrated on Cepheids come from Hubble Space Telescope. Hubble Space Telescope gives us the local galaxies that we use as an anchor. It gives us the galaxies that have Cepheids and supernova to calibrate the supernova, and it gives us the galaxies out there that have only supernova. So using the data from the Hubble Space Telescope, we can do this whole process. Okay, so what do we get for the Hubble constant if we do this whole process? This has been getting better and better over the last few years. The current value that we have for the expansion rate of the universe using Cepheids and supernova comes from what is known as the Shoes collaboration. It is actually SH0ES, but people pronounce it Shoes because saying SH0ES is harder and it looks like it says Shoes, so we call it the Shoes collaboration. So using the Shoes collaboration, using Cepheids and supernova from the Hubble Space Telescope, find a value of the expansion of the universe of 73.2 plus minus 1.3. What does plus minus 1.3 mean? This is the uncertainty. This is our degree of belief in the measurement. And any time you're doing any type of science, you're going to have this degree of belief. You also have this anytime you do any measurements at home. If you have a kitchen scale that has 1 gram precision, then you're never completely sure. If it tells you, you have 100 grams of ice cream, you might have 99, you might have 101. You probably don't care. 100 plus minus 1, that's okay. You might also see this, for an example, if you're going to go catch a bus or a train, and it tells you it's 1 minute away. Does that mean it's 1 minute 39 seconds, 1 minute 5 seconds, or 55 seconds, because all of these will probably round up to being 1 minute on a screen that can't show seconds. So you always have this error that comes from the way you measure things and the unknowns in your system. So when we say the Stu's team measured 73.2 plus minus 1.3, the 1.3 is the degree of belief in this measurement, which means from Stu's value, this could either be anywhere between 71.9 and 74.5. This is the range, but the most likely value is the one in the middle, 73.2. But it could be anywhere between 71.9 and 74.5. So this is what you get using the whole supernova, Cepheids, Hubble Space Telescope. This is a method you get. Comment from Abyss, I wonder if aperture size has something to do with resolving supernova in distant galaxies because lateral resolution depends on aperture size. Yes. And there was also a comment from John before about crowding. So I made a note of that. I know I didn't answer it when you asked, John, but you asked a question about Cepheid crowding. So one of the problems in the Hubble Space Telescope data is when you get an image of a galaxy, it's pretty impressive. Distinguishing individual stars is going to be messy. And sometimes you can have the problem that you have a Cepheid, but there's a lot of stars in the nearby neighborhood as well. So this adds to a crowding effect where the Cepheids are not alone. They have a lot of information around them, and this can leak in so that when you measure the Cepheid, you might not only be getting the Cepheid, you might be getting a bit of stuff from around the Cepheid as well. And this becomes a problem. The more stars you have, the more crowded your data set is, the harder it's going to be to make more precise measurements. Hey, Arlo, great to see you. Great to see you here in the chat as well. Comment from Bertha, you do care if my 100 gram ice cream is 99 grams. Well, do you notice 1 gram difference? Probably not, but you'll know. And the Swiss and Japanese care about how many seconds early or late their tram is. Probably. Yeah, I think about this sometimes when I'm going to the train or going to catch my bus, because buses in Helsinki, a tangent, digression time. Buses in Helsinki are overall very, very good, with the exception of one particular route that has a bad reputation, and it's the one I take to work every day. And it takes me 3 minutes to get to the bus stop. And I always check before leaving the house. It's like, the bus is 4 minutes away. I'm like, okay, it is somewhere between 2 and 6 minutes away. Let's go there. And then you get to the bus stop and somehow the bus is 12 minutes away. Anyway, then I always think about the uncertainty in the measurement. Like if it's telling me it's 2 minutes away, should I run? Is it actually 1 minute and 30 seconds away, or is it 2 minutes, 30 seconds away? Because depending on the answer, I either need to run or not. Alternatively, I should just leave a few minutes earlier, but nah, that doesn't happen. Okay, so there's a lot of things that can go wrong with this measurement of the expansion rate of the universe using Cepheid, supernova, Hubble Space Telescope, all of this. But it is something we have been doing for years, and we have really, really good precision on it. But now let's take a completely different approach and ask a good question of how else can we measure the expansion rate of the universe? So then we get into the idea of how can we measure how fast the universe is expanding? Well, how fast the universe is expanding is going to depend on our cosmological model. How do we measure our current cosmological model? What if we could get information about the very, very, very early universe, get information about what the universe was made of, the size of the universe, the age of the universe? We could use that information and project it forward to get an idea of how fast the universe is expanding today. We have a tool for this. Those of you who have seen Cup of Cosmology before, I hope you know where I'm going with this. We have a tool for this known as the CMB, the Cosmic Microwave Background Radiation, my favorite thing in the universe. So the CMB, the Cosmic Microwave Background Radiation, is a snapshot of what the universe looked like 380,000 years after the Big Bang, or after the end of inflation. Now, in the early universe, there were 3 main components. There was dark matter doing its own thing, but then there were 3 main components. There were protons, there were electrons, and there were photons, which are particles of light. All of these 3 things were constantly bumping into each other. As the universe cooled down, the protons and the electrons could combine together to form neutral hydrogen, which means the photons, the particles of light, broke away. They got left out, so they started traveling freely throughout the universe. They have been traveling ever since. Today, we can still measure these photons, this background radiation that is everywhere in the universe. Because it has been traveling for a very long time, it has redshifted into the microwave range of the electromagnetic spectrum, So it is tiny, tiny, tiny waves that are behind everything in the universe, these particles of light behind everything at the background, everywhere in the microwave range, which is why we call them the cosmic microwave background radiation. What we plot in this image here is the temperature of these photons. So this is basically a sphere centered around us. It's just pulled out in this random shape. And of course, it took 36 minutes, but you knew this had to appear. You knew the CMB had to appear. So if we're looking at this map, what we're looking at is the average temperature of these photons, of this light everywhere in the universe. This light is at approximately 2.73 degree Kelvin, which is minus 270 degree Fahrenheit, and minus 270 degrees Celsius and minus 440 degree Fahrenheit if you wanted it in freedom units. It is 2.7 degree Kelvin. But there are tiny, tiny, tiny temperature differences here. You can see there are some bluer spots and some orange spots. So these are tiny temperature differences. And we're talking differences of 1 part in 100,000 here. So 100,000th of a degree warmer or cooler, which is ridiculously small. But by measuring this map here, the CMB, this cosmic microwave background radiation, we get the statistical properties of the early universe. So this gives us an idea of what the universe was made of and what the universe was doing 380,000 years after the end of inflation. So 380,000 years after the end of inflation means 13.5 billion years ago from our perspective, which is a long time ago. From the CMB, we can get the amount of matter in the universe, the amount of dark matter in the universe, the amount of dark energy, basically what the universe is made of. But from the CMB, we get the best fitting cosmological model, which is lambda CDM. Lambda CDM tells us that the universe is made up of dark matter, about 25%, normal matter, about 5%, and dark energy, about 70%. This is what lambda CDM tells us. Lambda is the dark energy component, CDM is the cold dark matter component. This is our standard model of cosmology. Using our standard model of cosmology, we can calculate what the Hubble expansion should be today, what the Hubble constant should be today. So this is not a direct measurement. We don't look at this map and say, okay, based on this map, this is how fast the universe is expanding. What we say is, based on this map, this is my standard model of cosmology that has exactly 26.2% dark matter and 68.9% dark energy and 4.9% normal matter. And then you use those numbers inside our standard model of cosmology, inside lambda CDM, so lambda CDM with these numbers, to predict the value of the Hubble constant. Now, here's the controversial thing, should we call it a prediction or not? Because it is a prediction that our model is making, but it is based on observational data. So once you have measured the CMB, you can predict the value of the Hubble constant, assuming lambda CDM is correct. Lambda CDM being our standard model of cosmology, which we've inferred from the CMB. Okay, so when we measure with supernova, with Cepheids, we're measuring in the local universe, we're measuring today. When we use the CMB, we are measuring 13.5 billion years ago and projecting forward. How amazing would it be if these two measurements completely overlapped? It would be pretty cool, right? Well, they're close, but not close enough. So if we measure the expansion rate of the universe from the CMB, we get a value of 67.4 plus minus 0.5, which means it is somewhere between 66.9 and 67.9. So both of these values, the supernova one is about 73, the CMB one is about 64. They are pretty damn close. We got very close, considering that we just predicted across 13.5 billion years of cosmic evolution. We got pretty close, but not close enough. Because in science, pretty close is not good enough. And here is where that degree of belief in the measurement matters. Because if I said one is 67 plus minus 5 and the other is 73 plus minus 5, they would overlap. There would be a region where you could explain both. But they don't. Over the last 10, 15 years, we've got more precise data from the CMB, and we've got more precise data from the Cepheids and the supernova, where they've been able to figure out a lot of the problems with the supernova and Cepheids. It has not brought these measurements together. It has actually pushed them further apart. So now from the CMB, we get a value of 67.5 plus minus 0.5. So it is somewhere between 67 and 68. Shoes, the supernova Cepheids tell us that it is somewhere between 72 and 74.5. They're close, but not close enough. The chance of this being a statistical fluke is at this point 1 in a billion. So this is where we get to the problem known as the Hubble crisis, the Hubble tension, because these measurements, these different ways of asking the same question are giving us different answers. So what is going on here? Why are we getting slightly different answers? And we can use our degree of belief in these measurements, these error bars, this uncertainty, to quantify how far apart these are. And, you know, if they're just like this, you'd say, okay, they almost touch, they're like 1 sigma apart. If they're like this, they're 2 sigma apart. Sigma is the degree of belief. By now, these two measurements are what we call 5 sigma apart. This signifies a breakdown of something. This has been the state for quite a while now, because the measurements keep coming out and this tension does not want to go away. Okay. Back to the questions here. Just want to answer some questions here. There were people laughing about the drivers. Yes. Yeah. Comment from Scott: your drive to work can vary from 10 to 20 minutes. That's 100% margin for error. That is correct. Yes. Okay. Speaking of resolutions, comment from Abyss, I wonder how difficult it is to implement super resolution microscopy in space to resolve past the diffraction limit. Difficult for sure, but I think doable. I'm not completely sure I understand the question there. We are going to be limited by the technology, but even with all the different ways we're doing this, like considering the supernova and the Cepheids and Hubble Space Telescope, the uncertainty is quite small. You know, we're not saying it's 73 plus minus 20. We're saying it's 73 plus minus 1.5. That is pretty good. That is pretty good. In terms of science, that is pretty precise. You know, the CMB one, the one that we predicted across 13.5 billion years, gives us a value of 67.5 plus minus 0.5. This is pretty good. Okay. Comment from Fortunine here. Could the measurement of accelerating expansion be that we are at a cool, dense state, measuring photons from a hot, less dense state? That is a very interesting proposal. It doesn't seem to be the case. So a lot of people have looked at different ways of solving this. Could we be in a special patch of the universe? Could our local universe be different? And it doesn't seem to it doesn't seem to solve the problem. Why should our patch of the universe be different? And if it is, why? How is that affecting the Hubble constant? So that is a very good thought, but it's one that hasn't led to a conclusive answer just yet. There's a comment here from Abyss about WMAP that I do want to get to in a sec. But comment from Prathia: what if just the fact that you're asking this question in different ways inherently leads to different answers? That is not a very satisfying answer in science, because you should be able to ask the same question in different ways and get the same answer. You know, if I ask how fast does this pen fall, it doesn't matter if I'm doing it here, if I'm doing it on Everest, or if I'm doing it in a spaceship. We know there's a gravitational difference. We can account for this. But then the gravitational constant that we measure should be the same. Whereas here, we're asking how fast is the universe expanding today? Doing this measurement in different ways should still lead to the same answer to how fast the universe is expanding today. And it shouldn't be that we get different answers depending on who's asking the question, because science needs to be reproducible. And if science is not reproducible, it's not testable, it's not valid, it is not a complete description of reality. So then there's the question from Abyss about WMAP, the predecessor of Planck. And I actually want to get to that one, but let me just go to a specific slide. And I want to show you how the measurements of, I know this is still the CMB. I want to show you how the measurements of H0 of the Hubble constant have changed over time. So what you can see here on the vertical axis is the value of the Hubble constant, this H0, the expansion rate of the universe. And on the horizontal axis, you can see the year. You can see this as a function of time. And in fact, let me just put myself to the side here so that I don't get in the way of the figure. Okay, so you can see here publication year, so the year when these results were published. And on the vertical axis, you can see the values. So starting in the early 2000s, there was this measurement. You see there's two different colors here. There's the blue one called distance ladder, and there's a red one called CMB. The distance ladder is using Cepheids, supernova, all of this, where you're creating a ladder of distances. And the CMB is, of course, the CMB values. The width here gives you your degree of belief. So you can see in the early 2000s, when we had the first distance ladder measurements using supernova and Cepheids, the value was 72 plus minus 10, which was good for the time, but not good enough. Then you can see that the blue ones have gradually gotten more and more precise and have tended to a value of 73.4, which or 73, which is the value we get today. Whereas the CMB ones had a slight difference at some point. The first ones are the WMAP ones. This was the CMB mission that came before Planck. And you can see at first WMAP was around 73 as well. In fact, even the last data release from WMAP, known as P9, was also around a value of 70, 71. But then when Planck came in with P13, P15, P16, P18, you can see the value dropped. So it does seem like there was a slight difference between the WMAP values and the Planck values. And this is a solved problem. This is not the cause of the overall tension. It just seems like there was a slight calibration issue in the results from WMAP. And accounting for them, you can now redo the analysis using WMAP data, and you recover a value that's a bit lower. But it is interesting to note that, of course, the CMB measurements rely heavily on Planck. There have been measurements since the Planck times using other CMB missions, ground-based ones, like the Atacama Space Telescope or the South Pole Telescope, which are in agreement with Planck. But you can see here that now where we are today with P18 and the latest SHOES measurements, these do not overlap. They are very, very far away. There is a big white gap between them. There is a big white gap between them, and this is a problem. So how do we get these two to come back together? How do we solve this? And you can see here on the right-hand side, it says these are 5.3 sigmas apart. This means that the chance of this being an accident is like 1 in a billion. This is the crisis in cosmology, as people call it, the biggest question of our times. Depending how dramatic you want to be, this tension has many, many different names. So some questions here. Following on with Bradley's question of what if we just get different values because we're doing the measurement differently. So going back to the example of the pen, how fast the pen falls down is relative to the observer. That is absolutely correct. Someone free falling with a pen would say the pen isn't falling at all. This is correct. But this is something we can account for. We can change our frame of reference. We can imagine ourselves in the other person's frame of reference, and we can bring these values together if we know what is happening. And this is also what we do. When we measure CMB, we are measuring billions of years ago, and then we are predicting it forward to bring it onto the same time measurement as today. So we can use the fact that light travels at a constant speed in the universe. This gives us an absolute reference frame. This is true today. The speed of light today is the same as the speed of light in the early universe. This gives us something that we can use to map these two together. So we can use how the CMB looked 13.5 billion years ago, get the Hubble constant there, or the value of the expansion rate of the universe 13.5 billion years ago, and predict that forward. So we bring things onto the same measurement time, onto the same measurement frame. So technically, even though we are doing the measurements in vastly different ways, they should agree, because we're constructing it so that the CMB measurement should give us the value that we get, the value today, the local value in our universe today, which is what we are measuring from the CMB. From Cepheids and supernova. So then there's a question of, just comment here from John, does that mean that they overestimated the accuracy of WMAP at the time? It wasn't the accuracy that was overestimated, it was just one of the calibrators. So those measurements just shift down very slightly. The accuracy was still good. It was just the way that they were kind of calibrated, or the offset was something that has since been corrected for. So it's not a big problem. People don't think that WMAP and Planck are in disagreement with each other. The general consensus is that WMAP and Planck do actually agree pretty well with each other. Okay, now let me go back to the proper view, because I've made myself a bit small and I wanted to, there we go, that's better. Okay, so Hubble tension. What could be the cause? We have four main options for what could be the cause of the Hubble tension. And if you hear clicking, it's because I accidentally left it on the slide at the back, and I know I now want a slide at the beginning. Oh fuck, I don't. I want the slide anyway. Slides I'll figure out in a minute. So, four possible explanations for the difference in the Hubble tension. One of them being this is just a statistical fluke. We're doing two different measurements. Maybe there's just a random fluctuation, statistical problems, that means that we're getting different values. But given how precise these measurements are, the chance of it being a statistical accident or just chance is 1 in a billion. So that's not good odds. You probably don't want to assume that it's just a statistical fluke. So then there's three other possible ideas here. Number one is maybe there's a problem with the way the supernova measurements are done. Maybe Cephei supernova, Cephei supernova, maybe Hubble Space Telescope. Maybe there's a problem there in the way we're doing the measurements. Maybe we haven't understood Cepheids as well as we thought. Maybe we haven't understood supernova as well as we thought. Maybe there's a problem with Hubble Space Telescope data. People have been looking at all of these possibilities and haven't found a solution yet, but that is a question we must ask. Another question we must ask, or option number three, so we've got a statistical fluke, problem with supernova, problem with Planck. It's the next obvious thing. What if the CMB measurements are wrong? What if there's a problem, especially because we saw that there was this issue with WMAP and Planck being slightly misaligned. They are still compatible with each other. Maybe there's another problem. But there's a lot of ways we can redo this. We can also use things independent of the CMB. We can use the amount of elements in the early universe to get a similar number. And we also get this low value. So there are other ways you can do this early universe measurement that don't require Planck data, and you tend to get the same number. Option four. This whole process of taking the CMB value and projecting it forward to today relies on a cosmological model, the standard model of cosmology. So of course, option four is what if this is the wrong model? What if the standard model of cosmology is not actually the correct description of reality? What if there's more than just dark energy and dark matter in the universe? And this is where a lot of work has been done over the last 10 years, because there's so many ways you can try to solve this. But the problem is the CMB measurements are in such good, like lambda CDM, our standard model of cosmology, is in really good agreement with CMB, with the distribution of galaxies, with how light moves around galaxies. Every measurement we've done in the universe tends to support our standard model of cosmology. So if you want to break this model enough to solve the Hubble tension, you have to make sure you don't break it too much that you mess up everything else. And this is a very difficult game to play. And people have looked at countless models, myself included. I have 3 or 4 papers looking at exactly this, of what if we make dark matter bump into things? What if we make dark matter bump into dark energy? What if we make dark energy decay into dark matter? What if we make dark matter decay into light? None of this solves the Hubble tension. Some models get you close. One idea is, what if dark energy turned on in the early universe, then turned off and is now turned on again? That gets you close, but not close enough. So there are many, many different ways you can try to break the standard model of cosmology to try to explain this, but none of them have really convinced the community because none of them do a good enough job. And again, if you want to solve it, you can't mess up other data. You can't fix a problem in one data set by making it worse with everything else. If you solve the Hubble tension, but you can no longer explain why the CMB looks the way it does, you haven't solved it, you've shifted the problem. Okay, so we haven't found a convincing model. CMB data seems to be pretty good. Planck supernova data seems to be Hubble Space Telescope seems to be pretty good. It's unlikely to be statistics. Where do we go from here? Okay, so now 55 minutes in, we can get to the point of the stream. All of this was the introduction. Now we can get to the point of the stream. So MOND, as Abyss is saying, don't forget MOND. MOND is the idea of the modified Newtonian dynamics, which tries to explain why things look like dark matter without having dark matter in the universe. Unfortunately, Mond can't explain why the CMB looks the way it does. It can explain the motion of stars around galaxies, but it can't explain the CMB, and it doesn't solve the Hubble tension. People have tried, doesn't work. People have tried to change gravity, doesn't work. People have tried to add magnetic fields in the early universe, it doesn't work. People have tried thousands of things to solve the Hubble tension. We can find models that reduce the tension, but we have not yet found a model that solves it without messing up something else. This is a problem. So now, what if we redo the whole supernova Cepheid thing using something that is not Cepheids to calibrate the supernova, and using data that is not from the Hubble Space Telescope, which we can now do because we have the JWST, we have the Just Wonderful Space Telescope. So this leads us to the Chicago Carnegie Hubble CCHB, Chicago Carnegie Hubble Program. CCHB are a group of people, as the name implies, in Chicago and Carnegie, who have Carnegie. I have no idea how to pronounce that one. It starts with Carnegie. The CCHB. It's a group of people who were pioneers in terms of using Cepheids. They did a lot of work in the early days of how to clean up Cepheids, how to calibrate on supernova. They've been heavily involved with the SHOES team as well. But now they're doing an analysis where they do three different things. So the first thing is they use I see there's a very interesting conversation here going on between Abyss and Prath. I assume you guys have it covered. It looks very interesting conversation about the way light moves in the universe and decoupling. Decoupling is the CMB, the photons of the CMB breaking away. Just adding that there to your very interesting conversation that I'm trying not to follow because it keeps distracting me. But excellent conversation. Keep it up, guys. Okay, so CCHB have now proposed, what if we ignore Hubble Space Telescope data and instead we use data from JWST? And not only Cepheids, Carnegie Mellon University is my alma mater, by the way. Then you probably know how to pronounce it a lot better than I do. But that is very cool of this. So, using JWST data, what if we could use something other than Cepheids to calibrate the supernova? And in fact, there are other things we can use, which we couldn't use before because we didn't have the right data for it. People have found basically three types of stars you can use as this calibrator. One of them being Cepheids, stars that have a specific brightness. You can use this brightness and the period of the brightness to get the distance. You can also use stars that are carbon rich. These stars are known as something like JAGB stars, so we just call them carbon stars. These are stars that have burnt up all of their hydrogen, they've burnt up all of their helium, so they start burning carbon. Basic principle of a star is you burn hydrogen to make helium, you burn helium to make heavier elements. You gradually make heavier and heavier elements. At some point, if you run out of hydrogen to burn, you move on to helium and so on. Carbon stars are stars that have used up most of their light elements like hydrogen and helium and start burning carbon. When they do this, they emit a specific flash of light, which is known as the carbon flash. This is short-lived but has a specific brightness. So it's also something we can use in the same way we would use Cepheids. We weren't really able to find many carbon stars in Hubble Space Telescope data because it was too clouded, it was too crowded, it was too messy, but they are something we can find in JWST data. And another method is using TRGB stars, tip of the red giant branch stars. These are red giants that also have a specific amount of light that we can model. With JWST data, we can do the whole analysis with three different types of stars, with Cepheids, with carbon-rich stars, and with tip of the red giant branch stars. Now, the nice thing is these different types of stars are in different parts of the galaxies. So in the same galaxy, you can find all three of these types of stars, some closer to the center, some closer to the edge. And this allows us to get rid of some of the issues with Cepheids, because Cepheids are always going to be in a similar area of galaxies. Whereas with this, we can get rid of some of the background information, we can get rid of some of the crowding effects. So the idea of the CCHB was to redo all of this process using these three different methods and using data from JWST. So they're going to do the Cepheid thing, the same as the SHOES people. They do carbon stars and they do tip of the red giant branch. Now, they still need to do the three-step process here, where first of all, They need a galaxy close by that has all three of these types of stars and that we know the distance to. Once they know the distance to it, they can calibrate all of these three stars. Step 2, they find galaxies that have both supernova and these three types of stars. Then they can calibrate supernova using these three different methods. And then they use the galaxies that are further out there that have supernova. For the first thing, they're going to use one galaxy because so the JWST team have many different anchors, many different galaxies where they can measure the distance to and find Cepheids. But all of this proposal with the CCHP people is very new. So we still don't have a lot of these galaxies that have all of these criteria. So this means that they're only going to have one anchor point. And for the second step of the process, where they find galaxies that are close by that have all three of these stars plus supernova, they have 11 of them. So whereas the JWST team have about 19 anchors, about 52 in the second rung, in the second section, and then about 300 supernovae, the CCHP people have one anchor, 10 middle galaxies, and then about 200 out there. So the amount of data they have is a lot smaller than with the Hubble Space Telescope. But it's very cool because it's removing Hubble Space Telescope and using JWST, and it's using three different methods. One of them is Cepheids, so we can directly compare to the JWST measurement, and the other are two different methods. So this is the result that was presented in August by, the paper is called The Update of the CCHP Program, and is where they present their first major results using JWST and these three techniques. I'm going to go to comments and then present the results. Comment from Prathia, you like what For All Mankind did with JWST? They called it the Thomas Paine Space Telescope and launched it in the early 90s. See, For All of Mankind is on my list of things to watch. I just haven't got around to it yet, but I have heard really good things about it. Comment from Scott, around here we pronounce it Carnegie or Carnegie. Okay, nice. Good to know. I have no idea how to pronounce it. I'll just pronounce it. The CCHP is easier. Question from James, would a missing dimension be helpful, or is this just sci-fi? People have tried with missing dimensions. So we know that we live in a 4-dimensional universe. You know, we have up, down, left, right, in, out, 3 space dimensions and 1 time dimension. I know Prath is very interested in what happens if you add a second time dimension. General consensus around the office is, please stop asking me this question. I don't know. So I'm still trying to get an answer to that. But for now, we live in a 4-dimensional universe until someone wants to calculate a 5th dimension. We've only found 4 dimensions so far. But there are ideas that there could be extra dimensions that are rolled up in different ways or hidden. Extra dimensions are also a candidate for dark matter. Doesn't solve the Hubble tension yet. Every model people have tried, extra dimensions, dark matter doing different things, do not work. People have tried adding extra time dimensions as well. It does not solve the Hubble constant problem. It does not solve the Hubble tension. Okay, so CCHP results. They tried their 3 different, I'm still pronouncing the G like a J. It's Carnegie. Right, it's a G, not a J. That makes more sense. Carnegie. Okay. That makes more sense. Carnegie just sounds nicer. But okay, Carnegie. That makes more sense. Thank you. Okay, so CCHP results using 3 different methods. Just a reminder, the CMB value is 67.5. The JWST value, the supernova value that we're trying to reproduce is 73.2. So we have 67, we have 733. Results from the CCHP value. So first of all, using the carbon stars, these stars that flash with a specific amount of carbon, they get a value of 68 plus minus about 3. Off to a good start. This is closer to the CMB value. Using the tip of the red giant branch stars, they get a value of 70 plus minus about 2, which is still compatible with Planck, or compatible with CMB, but not compatible with the JWST measurement. Using the Cepheids, so the same method that has been used by the JWST team, but using JWST data, they get a value of 72 plus minus 2 or 3. So there are 3 different methods, give them values of 68, 70, and 72. Then they do the step of putting all three of these methods together, and the value they get is 70 plus minus 3. Sorry, plus minus 2.5, which means they are if we go back to the measurements and the uncertainties, if we say this is CMB, this is shoes, the new results are kind of over here. So they are close to the CMB ones. They are close. They're kind of in between, but slightly closer to the CMB ones. Now, this is very interesting. When this came out a few months ago now, or 2 months ago, 1.5 months ago, 6 weeks ago, made a huge splash because they reached the conclusion that based on JWST data, they do not need, there is no Hubble tension. They do not need new physics to explain it because they are compatible with the CMB value. Using JWST data, they are compatible with CMB value instead of with the shoes value. With some caveats, of course, they had 3 methods. The Cepheids method was very close to the Cepheids used by the Hubble Space Telescope. They have also broken down their analysis, and at the level of calculating the distances to individual things, HST and JWST are in very good agreement. So it doesn't seem to be a problem of changing the telescope, because every other check other people have done and they've done show that HST and JWST are in excellent agreement. However, when calculating the distances, it is discrepant, it is different. And they emphasize that this is not just at the level of calculating the distances to supernova, but already just comparing their own measurements, they say that their tip of the red giant stars and their carbon stars lead to lower values of distances than Cepheids. So one comment they make there is it seems like the Cepheids themselves are what are pulling to a slightly higher value. It's not the Hubble Space Telescope data in general, but of the 3 methods they've used, 2 seem to be quite low, and 1 seems to be a bit higher, which is the Cepheid one. So they concluded in their paper that we do not need new physics to explain our results. Basically, from their perspective, they are in pretty good agreement with the CMB, so there is no tension. So you can imagine how that went down in the field after people have spent years trying to solve the tension, and this paper is basically saying, we don't find a tension. Ooh, when this paper came out, then there was the interesting thing that the results of this paper actually leaked 4 months ago. So we knew this was coming. But when the paper came out, this is why there was a rapid response workshop, because if this is true, all of us who have written grant proposals of I'm going to solve the Hubble tension, what Hubble tension? So this is very exciting. Let's put a pin in this. I'm going to answer some questions here. Prath, yes, you want me to keep bugging people about the extra dimensions? Don't worry, I am. I'm also bugging people about white holes and Hawking evaporation. I have updates on that one, but that's for next week. Okay, comments here. Do they know why the Cepheid measurement seems out of alignment with others? This is one of the questions. Their main answer is that Cepheids suffer from crowding. There is a lot of data in the background that can crowd Cepheids, but they can't really explain why their results are different to the shoes team yet. I'm coming back to this in a minute. But they can't really explain it, but it does seem that in their results, the red giant stars and the carbon stars shift slightly lower than the Cepheids, just at the level of distances before we even go to the Hubble constant. Comment from Prath, is this carbon flash thingy covered in more mainstream channels anywhere? I want to know more about it. Yeah, I think there are people talking about it, but people just kind of leave it as a star that has a specific splash of carbon. And it's not something that I want to get too in detail in because it is very astrophysics heavy and it's not something I'm well versed in. But if you search for JAGB or carbon stars, you will find things for this online. It is something that you can find explanations for online. Okay, hey Guadav, great to see you in the chat here as well. I see we also have a comment from Mabis. Do you think gravitational wave astronomy could also help in aiding the cosmological ladder approach? Yes, absolutely yes. Let me put a pin in your question there about gravitational waves, because that is one I want to answer. And I think I wrote down two questions. Is H not varying in space? I answered that. It's not varying in space. That's something people try to solve the Hubble tension. Doesn't work. Even if you say we're in a local void and the Hubble constant is different here than it is over there, doesn't solve the problem. Problems with Cepheids, we talked about the fact that there's crowding, about the metallicity, about the dust. There's a lot of these issues. And this is why we have these other ways of doing it. Okay. More questions here. I see there's still this discussion going on about the speed of light. Very cool. Wasn't there a JWST study last year that looked at crowding specifically and said it made the tension worse? Indeed. Indeed, there is. So it very much seems like crowding is a controversial topic with Cepheids, depending on how you do the analysis. Basically, what it can do is either increase your distance slightly, decrease it slightly, or increase your error bars. So it is a big problem. But it is a problem that isn't enough to explain the full Hubble tension. Even if you play about with crowding, you can shift the Schu's value from 73 to 72, but it doesn't get you close enough. Okay, so there was this paper by the CCHP team that was basically like, we don't see a tension. JWST data using these three different methods, we don't see a tension. Some things have happened since then. So of course, when these results were presented, there was a lot of backlash. These results were not immediately embraced as we solved the Hubble tension, let's go home, because science needs to be reproducible, it needs to be scrutinized, and especially when there are different teams getting different results. You can't just say like, okay, let's go home now, tension solved, we're done. That's not how it's going to work. So there have been a couple of points of criticism about the analysis. The first one that is something that didn't sit right with me, and a lot of people have complained about. So they have these three different methods, but these three different methods all rely on the same group of galaxies. So is it really fair to combine the results? So when they have their values of 68, 70, and 72, is it fair to combine them together, given that it's basically the same data? Are they double counting? So yeah, they combine their results, and it's a question of should they actually have combined all three of their results, given that statistically they are triple counting here. They're artificially reducing the uncertainty. So even if we kind of ignore the fact that they combine their data, we can just take the three numbers individually, right? We can take the 70, the 68, the 72, the three different approaches. The combination of them has some statistical concerns. The bigger point of criticism, and there has already been a response to this paper, not just at conferences and at discussions. There have been some very heated discussions, but the Schu's team put out a response paper, a paper kind of responding to the claims of the CCHP paper. I'm going to get there in one sec. Coming from first, did you cover the cosmological ladder already? The cosmological ladder, so the distance ladder is another way of explaining these three-step processes that we do. We call it the distance ladder, and it's where we take the measurements close by, then we calibrate Cepheids, then we calibrate supernova. This is the distance ladder. And when we talk about the cosmological ladder, we are also talking about using CMB to project forward. So rather than creating standard candles, we use a standard ruler, which is the size of the CMB peaks, and we use that to project forward. So you can say this, I don't think I use the exact phrase, but distance ladder is when we calibrate Cepheid, supernova, or whatever, and supernova. Cosmological ladder is when we use quantities of a known size, like the size of the CMB peaks, or the bumps in the CMB. We can use that size to predict it forward to today. So that's the cosmological ladder, and the distance ladder is using local distance measurements. And these are the two different words. There's a lot of different ways of calling these things: the Hubble tension, the distance tension, the calibration tension, but it all comes down to the same thing. Comment from John here. If it holds up that there was an error at the base of the distance ladder, what other things in cosmology might that affect? Could it impact other tensions like sigma 8? Excellent question here, John. So just briefly, the sigma 8 tension is another problem that we have in cosmology, where we look at how matter clusters how it clumps together on specific scales. And again, we can get this from the CMB in a similar way to the Hubble constants. And we can also get it from weak lensing experiments, looking at how light distorts around galaxies. And we get slightly different values. The problem is not as big as the Hubble tension, but it is what we call 2 to 3 sigma away from each other. So it is not as big as the 5.3 sigma. However, you can usually what happens is if you try to solve the Hubble tension, you make the sigma 8 tension worse and vice versa, because they both rely on the underlying amount of matter in the universe in different ways. So one of the big problems of trying to solve the Hubble tension is not making the sigma 8 tension worse. If this holds up, that there is a problem with the distances, it actually doesn't have any impact on sigma 8, because sigma 8 doesn't rely on distances at all. It uses weak lensing experiments. So even if it holds up that there was a problem with the way we were doing this distance ladder thing, it doesn't actually affect the sigma 8 tension. But that is an excellent question there. But, of course, the JWST team had to respond. They had to issue a response to this paper, giving their perspective. The big response that they give here is that, and it's something that I mentioned, that the CCHP people are using a very limited data set. Because they don't have access to more yet, JWST is still in its early days compared to HST, we still don't have a lot of data. They used 1 calibrator and 10 galaxies, which is not a lot of data. And something that the JWST team have pointed out is that the type of galaxies that they used are all very close by, because they're trying to find galaxies that have tip of the red giant branch, carbon stars, and the Cepheids, which means they're using very close by galaxies. So all of the galaxies that they use in their sample of 10 are very close by. And that means that they're not getting a full picture of how the universe is expanding. They're getting a very close by measurement. So what the JWST team have done is basically redone their own analysis, taking the same distance of, if we only took galaxies out to this distance, what would we find? And then they find the same as the CCHP people have found. So what the JWST people have then said, or what Adam Rees et al. Have then said, is that it's not so much that they're getting a different distance here, it's that their data isn't complete. And because they're only looking at an incomplete data set, they cannot get the full picture. Furthermore, if they redo the Hubble Space Telescope analysis, also taking the same subset of data, the same distances, they get the same value. So the response from the JWST people, or from the people working on supernova and Cepheids, is basically to say, you need more data to make the claims you're making. And when you get more data, let's talk about it again. So it's very, very cool, because another point of criticism that has been said is, like, we have these three methods, which is great, but TRGB and carbon stars are very, very new methods. Cepheids have been around for 30 years. We know what we're doing. We don't yet have as much credibility in the other two. We don't believe the other two methods as much, just because they haven't been through as much scrutiny. So, to recap here, measuring the expansion rate of the universe is difficult. We have a lot of different ways we can go about doing it. If we do a measurement from the CMB value, we get a value of 67.5. If we use supernova calibrated on Cepheids using Hubble Space Telescope data, we get a value of 73. The new team, or the new paper by the CCHP people, use 3 different methods: Cepheids, tip of the red giant branch, and carbon stars to calibrate their supernova. In all 3 cases, they get a value of the Hubble constant that is lower than what the JWST team find, closer to in agreement with Planck. However, they didn't use a lot of data because they don't have a lot of data yet. And the general point of criticism seems to be, if they use more data, they will once again be in line with the other measurements that have been done. Then there is also the question of, why didn't they use Hubble Space Telescope data as well? Like, part of the thing was to test different missions, but now that we know that overall HST and JWST do agree at different levels, why not combine the supernova or the local galaxies that we have from HST, as well as the ones from JWST, why only use a subset of the data when we can combine these? So the general thing is the CCHP people report that their results don't show a Hubble tension, but it seems like they didn't really use as much data as they need to make that claim. So it is very controversial. It is very exciting because we have one team saying maybe there's no tension, and another team saying like we don't trust your analysis, which is how science works. And one of the first questions I think John asked, like, were these results accepted? Of course they weren't. Of course, people aren't just going to say like, Hubble tension is solved, let's go home, job well done, guys. No, now we need to verify everything. The main thing is it's going to take a few years to get a conclusive answer because we need other missions to give their opinion. We need other things to weigh in and to comment and to respond here. There's still, basically, we need more data. And this is something we might get over the next few years. With JWST taking more data, we are going to get more galaxies that we can put in this analysis. And even if it turns out that the CCHP people, whatever it turns out that they find, if they find the CMB value or if they find the shoes value, it is still really important because they are developing these two new alternative techniques with the TRGBs and the carbon stars. So they are developing new techniques to do this whole measurement process, which is really cool because it adds another way of getting measurements. It adds another way of doing things. When we have a tension, when we have a crisis, when we have measurements that give different values, we need new techniques. TRGB carbon stars are very promising. Using JWST data instead or as well as HST data is very promising. There are a lot of avenues. The main takeaway for me of the last couple of this whirlwind of the last 6 weeks is that we need more data. You know, the shoes team did an incredible job. The CCHP people are doing an incredible job. Everyone is working really hard to check everything here. So I think realistically, within the next 5 to 10 years, we will find a solution to the Hubble tension. I really think we will. And it's extremely exciting. And now let me go back to a question that Abyss asked me a while ago. Do gravitational waves help? Do gravitational waves help? Of course they will. Gravitational waves are amazing. Gravitational waves are tiny ripples in the fabric of the cosmos caused by massive objects smashing together, or basically by anything moving in the cosmos. There are gravitational waves coming from many different things, including black holes smashing together, and importantly, neutron stars smashing together. The reason neutron stars smashing together are so cool is because when neutron stars, really dense stars made of neutrons, when these smash together, they produce gravitational waves, but they also produce a burst of electromagnetic radiation, so a burst of light. This means that it's something we can see across the whole electromagnetic spectrum and in gravitational waves. This is known as multi-messenger astronomy or multi-messenger cosmology astrophysics, and it's where you get information about the same process from different detectors, different types of detectors. Already with LIGO, Virgo, Cagra, with LIGO, we found this once, where two neutron stars smashed together and we were able to see the optical counterpart. So we were able to see the electromagnetic burst of energy in optical range, in gamma ray, in radio telescopes, across the whole electromagnetic spectrum. And this is really cool because this allows us to measure how fast light is traveling. We know how fast light is traveling. It's traveling at the speed of light. And it allows us to measure how fast gravitational waves are traveling, which also seem to be traveling at the speed of light. And this gives us a whole new method. We've introduced standard candles. We've introduced standard rulers, so objects of a specific size, like the CMB. Gravitational waves provide a standard siren. We know how fast a gravitational wave is going to travel. It's going to travel. We can measure this thanks to how fast, we can compare it to how fast light is traveling. So once we get many more data points of neutron stars smashing together, where we can also measure the electromagnetic part and the gravitational wave part, we can get a completely independent measurement of the Hubble constant. It does not depend on CMB physics. It does not depend on our standard model of cosmology. It does not depend on supernova, on Cepheid. It's a completely independent measurement that just depends on gravitational waves and general relativity, which we have a pretty good handle of by now. We have got one measurement of this that we got in 2017, and with this one measurement, they found a value of 70 plus minus 15. So anywhere between 55 and 85. It's not great, but that was with one data point. Imagine when we have 20 of these, or 50, or 100. Within the next 10, 20 years, we should get enough gravitational wave data that we can make a completely independent measurement of the Hubble constant using gravitational waves, which is very, very, very cool. This will be a whole new way of answering this question. There's other ways people are trying to answer this question using how light from quasars, like the brightest centers of galaxies, you can use how light from that is distorted to measure the Hubble constants. That is also very difficult to do, but people are trying to do this. So Hubble tension has been around for a few years now. It doesn't seem to want to go away. There's a new paper from the CCHP people saying that in their analysis of JWST data using 3 different methods, they don't find a tension. However, it seems like they didn't have enough data. So what we need now is more data, more measurement techniques, more ways of approaching it, and more collaboration. And this is all happening. So as Angie's just saying here in the comments, this is going to lead to more research. People are going to double, triple check again the Cepheid. People are going to scrutinize JWST data again. And we're going to keep looking at ways to solve the Hubble tension because it's amazing. And this is how science progresses. So it's been a really exciting couple of weeks for the Hubble tension. And even though we're probably not any closer to solving it, it feels like we're getting more pieces of the puzzle. So eventually we will get there. Going to some of the questions here, because I saw there were a couple of questions that I haven't yet answered. We talked about that one. I know there's still the interesting conversation about the speed of light. We talked about sigma 8. Okay, a comment from Guadav. You found some lost astrophotography data. That is very cool. Please do share the images when you create them. Tag me on social media if you make the images so I can see them, because that sounds very cool. Astrophotography is amazing. You have different nebulas. Very nice, very nice. Okay, comment from John. How does the expansion rate measured by Dizzy and Euclid compare? Excellent question. As of last year, or a few months ago, we have data from the Dark Energy Spectroscopic Instrument, which is measuring galaxies that are spreading out in the universe, and you can actually get a value of the Hubble constant from Dizzy, assuming a model of cosmology. So it also very much depends on the standard model of cosmology, and it's not an independent measurement because it also needs information from the CMB. You can't just use Dizzy alone, but you can use Dizzy data to get a value of the Hubble constant. It is in very good agreement with the Planck value, or with the CMB value. This is also the case when we use BAO measurements, so the average distance between galaxies that is imprinted in the universe. You can use this from different measurements, and they all tend to be in agreement with the CMB value. But again, they assume the same standard model, and it's also an early universe measurement as opposed to a local measurement now. As for Euclid, we don't yet have science results from Euclid yet. Rumors have it that January, March, early 2025, rumors say we might get a Euclid update. I can't give any more details than that other than I've heard rumors. I trust my sources, but we'll see. We will see. Okay, but yes, using the average distance between galaxies is an early universe measurement. We're looking out there. We're not looking here. And these measurements tend to agree with the CMB value. Question from John here. Can carbon stars and tip of the red giant branch be calibrated by parallax measurements? They can if they're close by enough, but the method that was actually used to calibrate them is using masers. So masers are stars that have water in the atmosphere. Water? Yes. And they produce specific bursts of light that allow us to get the distance. So the way that they calibrated the stars was not using parallax, although it can be done, but it was using a specific galaxy that has megamasers. So it was using this exact distance to the water stars to then calibrate the carbon stars to then calibrate the exploding stars. It's messy. But yes, if you want specifically, the galaxy that they use as the calibrator, I believe by memory, is NGC 4285, I believe. And this is one that has all 3 types of stars plus megamasers, which are stars with water. That's a thing, apparently, that you can use to get specific distances. So even though you could use parallax is the way stars or galaxies move in the night sky. We can use that to get accurate distance measurements. you can also use megamasers. Comment from James, I'm doing quick fire questions now because I have been talking for an hour and a half, so quick fire questions. One from James here, is there any criticism to the release or timing of the releases from JWST? Is there a lot of data in queue to be released? So cool thing and bad thing with JWST, it's a bit different to other telescopes or missions like Euclid, because the idea with Euclid or with DISI is the data is all towards one goal. So then it's processed together, all of the data comes in, it's processed, it's waiting time. This is the same with Planck, there's the queue. For JWST, you need specific observing time because JWST has hundreds of different goals. There were calls to get different telescope time allocated where you can basically ask JWST, can you point over there for me? Can you point at that? I want to look at this. This is something that requires telescope time. There's a lot of people doing a lot of very cool science with JWST, so it's quite hard to get specific timing. In order to get more galaxies, to be able to galaxies that have the carbon stars, the TRGB stars, and the Cepheids, we need more observing time dedicated to looking for these specific things. We were trying in this rapid response workshop, people were trying to ask the JWST team or the people working on the CCHP to commit to when are we going to get more data? And they were being very vague, like, well, it depends when we get more observing time, there's a lot going on. We're like, okay, but are we talking 2 years or 10 years? And after a lot of back and forth, one of the guys was like, don't quote me on this, and I'm quoting him on this. He's like, don't quote me on this, but maybe 5 years we'll have enough data. Of course, it very much depends. Now that this has gained a lot more interest, there's going to be more people requesting to point at these galaxies. So it's not that there's a backlog with JWST, it's not that there's data sitting around waiting, it's just that we haven't got the data yet. People are working on it. Again, JWST is an amazing mission doing a lot of really cool science. It has a lot of objectives, so it's not just focused on trying to solve the Hubble tension, but it is a cool thing that we can do. Okay, an hour and 32 minutes in. I hope we've convinced you that Hubble tension is a very, very, very cool topic, and the recent results are exciting. Whatever ends up happening with CCHB, whether it turns out that with more data they bring back the Cepheid value that Shu's found, or if they find the CMB value, whatever happens, it is interesting, it is exciting. It is really showing us the next steps. We need more data, we need new independent measurements of H0. And in the meantime, us theorists are going to keep dreaming up ways we can break the standard model to try to solve the tension. It is very interesting. It is very exciting. I've now given a talk about this at work, and then I presented one paper. People presented the counter paper. There's been 2 or 3 conferences on it already. And it's only been 6 weeks since the paper came out. So it is still early days. The paper has not yet been peer reviewed. It is undergoing peer review now. But the community is already doing community peer review. And this is why putting your results in a publicly available way is really important in science. Okay. I think I got through all of the questions. An hour and 30 minutes, and this time I didn't actually have coughing fits. My voice held up surprisingly well. So just going to conclude here and say that I am honestly pretty surprised. Those of you who've followed me for a while know that I have long COVID. I talked about this at the beginning of the stream. I just had an absolutely ridiculously busy week, and I didn't have a flare-up. And my symptoms are getting almost under control right now, which I'm super happy about. So that's just a minor thing there that I'm happy about. That the fact that I'm now not tired after doing this for 90 minutes is very cool for me. Minor personal info there. But yes, this has been super fun. Thank you for all the questions. We've had a lot of really interesting questions. I feel like some of you did your research ahead of schedule because you already came in like, okay, let's talk about clouding. Let's talk about this. I think some of you did your research ahead of schedule, which is great, because I had announced that this was going to be a topic. So thank you for that. And thank you for all of the questions. Even if you didn't do your research ahead of schedule, of course, that's not expected of you. I do the research and tell you about it. But if you do research ahead of schedule, then you ask me tough questions, which is really cool. Thank you everyone for joining. This has been super fun. At some point in the next couple of weeks, I'm going to do a stream about the paper that I put out in June that I just haven't had time to do a dedicated live stream about. That is going to happen at some point soon. And also, of course, towards the end of October, there will be a Halloween special, because of course there's going to be a Halloween special. I'm now booked in for like 3 Halloween parties. there will be a Halloween special towards the end of the month. There is going to be cool stuff coming. I've also got three visitors lined up. I just need to schedule with them. 2 or 3 visitors lined up, guests lined up. So more stuff coming with Cup of Cosmology. In the meantime, please do like the video, subscribe, leave a comment if you haven't done so already. As always, you can reach me at contact@cupofcosmology.com. If you want to chat about anything, just feel free to reach out. I'm not quick with replying to emails, but I do always get back to emails eventually. Okay, so Cup of Cosmology should be online next week, same time as always. That is 8 p.m. if you're in Finland like me, 7 p.m. if you're in mainland Europe, 1 p.m. if you're on the east coast of the US, 10 a.m. if you're on the west coast of the US. There is a time zone converter on cupofcosmology.com where you can figure out when the next live stream is in your own time zone. But the easiest way to stay up to date is to subscribe to the YouTube channel, subscribe to the Twitch channel, and then you'll be notified 30 minutes before I go live. And the streams always appear on the YouTube channel as scheduled at least 6 hours in advance. If they're not there 6 hours in advance, it's probably not happening. But Cup of Cosmology will be online same time next week. I hope to see you all there with excellent questions like today. It's great to have you all here. Great to have so many regulars and so many new people in. As always, thank you everybody for being here. It's really fun. I hope to see you all again next week, same time as always. And I hope in the meantime, you will take care of each other and stay curious.